All right, everybody. So we are going to begin our lesson and unit on force. And this particular lesson and video is dealing with force basics, so just kind of what is a force, and then free body diagrams, which is how we represent forces with vectors. So again, on your Google slide version of this, these are all links that will take you to different videos and ideas if you want to kind of gain some insight using those examples, you can. So I'm going to talk to you about a couple things, and the main goal of this whole chapter is to kind of tie in the idea of how forces affect motion. So in the last unit we studied motion and how things move and describing how things move, and forces are really the reason why things move. So the application of force is what causes the change in motion of an object. So we're in the first section, and I'm just going to start with my basic definition of what a force is. So a force is just a push or a pull acting between two objects. And forces cause objects to accelerate, so that's the big idea, is that forces cause things to change how they move. So when things are changing how they move, you see accelerations where the object starts increasing velocity, decreasing velocity, or changing direction. So those changes of velocity and how quickly that happens is the acceleration. But if you have any sort of acceleration, you have to have a force. So again, forces are just a push or a pull, and there are two important kind of ideas that go along with forces. There is a force that acts on an object, and then there is a force that is provided by an agent. So, and it can be in the same situation. So we're going to look at these examples up here that we have with our different people. And for this first one, so we want to decide what is the object that the force is acting on, and then what is the agent or the thing that is applying the force. And this isn't too hard, it's mostly just common sense. So if we look at this one, it looks like there's a woman shot putting. So the shot put is here, but I just drew that ball. So I would call that the object. So that is the object on which the forces are being applied. So the object is what the force acts on. And the person here, this person, who is throwing and pushing on the shot put, is the agent. So it is the cause of the force. And it's important to identify the difference between those two things because forces are caused by things and they act on something else. So in the second one here, this person is hitting it looks like a heavy bag with a punch. So the object is already labeled, that's the heavy bag. So that's the red bag there. And then the person here, this person is the agent again. So I'll just write A on him. And then finally, there's another one here. So the quarterback is the agent and the ball would be the object. So it's not really hard to identify these things. It's just like what is doing the pushing is the agent, and what it's pushing on or pulling on is the object. Okay. So we've talked about vectors when we talked about motion, so this should be somewhat review. But a vector we use again to demonstrate a measurement that needs an amount, a unit, and a direction. So forces are in direction, so that's why you need to have a vector to represent them. So arrows are used to represent vectors. So the larger the arrow, the bigger the force, the smaller the arrow, the weaker the force, and then wherever that arrow points is the direction of that force. We also group forces into two main types. So I'll define those really quickly. Oh, in general, we just use F for a force, and that's kind of the generic force, any force. Depending on which book or which person is teaching it to you. So F would be force, capital F. And then usually I write subscripts. So I might write Fn or Fg or Ft or Ff. Those are all the subscripts. So these are, we'll learn about what these are in a later video, but F just stands for force, and then the little subscript for me is what is causing that force or the type of force that it is. So you can, if we came back here to this person and the punching the bag, it would be the force of the man or whatever. You could just write that. Okay, or you could just say force applied. You can use some generic terms. You just have to clearly label and show that in a vector scenario. All right. So anyway, the two types of forces that we have, 1 and 2 here. The first one It's called a contact force, and the word contact means touching, basically. So any forces that are directly two objects touching, that is considered a contact force. So you can probably think of lots of contact forces. I will probably give you a question here about a contact force. And then there's a second type of force, which is the opposite of contact force. They're called long-range forces, or what I learned them as is they're called field forces. And those are forces that act without physical contact. So maybe I'll give you one question here that'll distinguish between contact and field forces, and hopefully you'll get that right. So anyway, that's just like grouping again. It doesn't really matter. We still draw vectors the same way. It doesn't matter if it's a contact force or a long-range force or field force. We still draw just arrows starting at the object. Okay, so here, if you look at this example, again, this book uses slightly different notation, so I would call this Ft for the force of tension, and F spring, yeah, and then F weight or F gravity for that. And then with vectors, they're talking about the tail of a vector. So if I draw a vector, the dot here is where the vector starts, and we'll have it going to the right like it does on these pictures. So this is called the tip of the vector, where the it points to, and then the tail is where it originates. So just so you know what that definition means. So it says all three tails of the vector are placed on the particle that represent the object, regardless of where the force is applied. So it's not where the force actually touches the object or acts on the object. It's really, we just all draw them at the same point, and that's easier to visualize what's happening. So in this example, we have a person, the first one here, we have a person pulling, trying to pull this box with a rope. So the rope is the object that is actually touching the box is the object. So we would just draw a dot for the box, and then we would draw an arrow going in the direction that the force is acting. So if they're pulling on the rope, it's going to the right here. And the pulling force on the rope would be Ft or T. I would label it Ft. And that's going to go to the right there. So that would be a good way to represent the force of the rope pulling on the object. Even though the rope is like on this side, we create a dot in the middle. We did this with the particle model with motion, so it's not that different. Same thing here with the spring. So like we have a different scenario. There's a spring pushing on this box. So the spring is the agent. That's the thing doing the pushing or pulling, and the box is the thing that's getting pushed. So we have an arrow going to the right again, because we're imagining the spring is, I guess, compressed, and it's starting to push this box to the right. So we have our pushing force of the spring, or the spring force, going to the right. If we talk about dropping the box or something, gravity, the force of gravity, or the weight of an object, so I would say Fg for gravity, is acting, and it's acting downward. And again, the gravity of the Earth is what causes the gravity of the Earth pulling on the box, but the Earth doesn't actually touch it, but we still just draw that dot in the middle, and we kind of identify the direction in which the force is acting. And then the size of the force is represented by the size of the arrow. Okay. So we're going to kind of get used to drawing figures similar to this. And these figures are really important in solving force problems. They're called free body diagrams. So FBD stands for free body diagram. And it's just a picture that shows all the forces acting on the system, or the object or objects of focus. So the system is our object, or objects if we have more than one, being applied by agents. So again, that agent is the thing that is doing the pushing or pulling, and the object is the thing that is getting pushed or pulled. In a free body diagram, all forces originate at that single point at the center of mass on an object, so we've been doing that. And let's try one for a book resting on a table. So if this red surface here, that's the table, that's the ground, and I'm just going to draw a book on it here. So here's a green book. Okay, so we need to think about the forces acting on the book, and the book is at rest on the table. So I'm just going to draw a dot to represent the book. So here's a dot. That represents our book. And we want to talk about the forces acting on the book. So what forces can you imagine that are acting on the book? And the first one that most people come up with is the force of gravity. So if anything is near the surface of the Earth, there's a force of gravity. And most people think the force of gravity pulls down. And when we get into specific forces, we will talk about that and clarify that a little bit. But Fg here is standing for the force of gravity. And I have just an arrow pointing down towards the bottom of the page. Now, if that was the only force acting on this book, the book would be accelerating downward, because it would if there's only one force, it's going to win the tug of war or the battle. So it would definitely go kind of down. But is this book falling down? And I would say no, the book is not falling down. And what's keeping it from falling down? The thing that is pushing it up, which is the table. So if I drew a force going up, and I labeled that arrow pointed upward as the force of the table. So you can just write F table if you want, because that's the agent that is acting on our object, which is the book. This table force, or this force pushing upward from the surface or perpendicular surface, this is known as the normal force. So in later problems, we'll refer to this as Fn for the normal force, and that's fine. So if I asked you how the gravity force and the table force compared, what do you think? Do you think one is bigger than the other? So do you think the gravity force is larger than the table? Do you think the table force is larger than the gravity? Or the other possibility is they would be equal. So what do you think is most likely in this scenario if the book is at rest? And the correct answer is that they should be equal. They should be equal because the box or the book is not accelerating. So because the book is just at rest here, there is no acceleration. It's not changing its motion. It's just staying on the table. Those two forces have to cancel out to make it so that it doesn't accelerate up or down. If one was bigger or smaller, then it would win. If you imagine this is sort of a tug of war, which is the way that I tell students to visualize forces. They're just tug of wars between things. Whichever one's bigger would win. So if gravity was bigger, it would start accelerating downward. If the table was larger, the force of the table was larger than the force of gravity, then it would accelerate upward, and neither of those things is happening, so they are equal. All right, let's try another one. So this one says a free body diagram of a book sliding at a constant velocity on a table. So basically the same thing, same book on the table example. So if you imagine that same scenario here, there's the table, and I'll have the same book. But this time, the book is moving. So there's some velocity associated with the book. So I'll draw like the motion cartoon lines, where it's sliding and you can see it going to the right. And we're just supposed to draw the forces. So if the velocity, let me ask this question, is velocity a force? So is velocity a push or pull? No, velocity is how quickly you are being displaced. So it is not a push or pull. So we don't have to draw that picture on our free body diagram. So when I start with the dot over here for the book, that dot represents the book, we don't draw an arrow going to the right because there is nothing pushing or pulling box right or left. So again, we just have the same forces. We have the force of gravity acting, which is pointing down, which deals with the weight of the object. And then we also have our normal force, or the force of the table. I'm going to write Fn just to get you into the habit of seeing that as a normal force. And it is the same scenario that they are in the exact same kind of proportion, so they are the same size, because if they weren't, then the book would start accelerating upward or downward. So if this is moving and it's moving at a constant, that means that there is no force acting right or left, because if there were, it would start accelerating in that direction. So it would start to increase velocity or decrease velocity left or right, and that is not what's happening here. So so this free body diagram that we just drew is the exact same one as the one we just drew in the previous example, but we have two different scenarios. So we have one thing that's at rest and one thing's at constant velocity. And we'll learn more about that when we get into Newton's laws and discussing those concepts. A couple more slides here. So as I mentioned, we're going to combine forces, and we started to do that with that last example and drawing the free body diagram. And again, I think the easiest way is to think of it as like a tug of war. So the overall effect of a group of forces is in the direction of the sum of all the forces together. So like when you put the forces together, whichever one is bigger is going to win, and the overall effect is called the net force. So we have an example here where we have a top view of two people with two ropes attached to an object. One rope is pulling up and to the right there in our frame of reference, and the other one is pulling down. So again, you could make this as simple as F1 and F2, which is what they do in the diagram down here. And we want to know what is going to be the overall effect, or the net force. In our previous examples, our net forces here were 0. So That's because they canceled out. These were balanced. That's another way to think about it. So if the forces are balanced, the net force is 0. If it is unbalanced, the net force is equal to some value, and that value is going to cause an acceleration. Okay? So in this example, they are not balanced because they are not going kind of opposite ways, and they're not in equal sizes. So it says the net force is sometimes called the resultant, so sometimes I'll use that terminology. It's not a new force, though. It's sort of like if you took these and combined them and just drew in one, that's what you would want. So that's the net force. So our net force in this problem, if this is going up and to the right and this is going down, then it's going to kind of go down and to the right. And the reason why it goes down and to the right is this force down, if we break this one up into components, so we did components with projectile motion again, and I look at this blue arrow going up, which would be F1 in our frame of reference, it would be in the Y. It is not as big as F2, which is going down, so down's going to win, so there's going to be some net force going down. And then going left and right, the green arrow here, which would be F1 in the X. That definitely wins because there's nothing canceling it out, so that's like F1 in the X. And then the difference between F2 and F1Y is what is left over there. And then, so that would be kind of this difference here. And we'll see this and practice with some numbers eventually. And eventually, like those two forces or components of forces added together will get you the net force, which is that red arrow. So it's going to go down and to the right. We could figure out the number if we had values. We're going to practice some. So this is a good way to start talking about it. Okay. So this is our free body diagram. We're just going to imagine the dot is there already, and these forces are drawn proportionally for the dot. So again, we have these different forces that are acting on these two different situations, and we're going to try to determine the net force or the overall force acting on the object. And if we do figure it out, we want to say which way it's going and how big it is. Okay, so this is pretty simple. So we have these four forces here. So gravity going down, excuse me, some applied force going to the right, the normal force going up, and then some friction force going to the left. So if you look at it, they give you values. So you can do this a couple different ways. I'm going to kind of preview the way that I would suggest you start doing it when we were dealing with math. But this one's easy. You can kind of see, oh, the up and down forces, and that's what we're going to look at. We're kind of separate forces into directions, just like we did with components of vectors, so x and y. So x is the horizontal stuff. So to the right is positive, and to the left is negative, and the x direction. Up and down would be the y. Up's positive and down is negative. And then all I would say is I really suggest you make these tables, and then you're going to draw or label all the forces here. So we got force gravity, so I'm just going to say Fg. We got the applied force, I'll just say that's Fa. The normal force, Fn. The friction force, which is going to be Ff. And I need to scroll down a little bit. There we go. And at the bottom of our chart, after we've listed all the forces that we see or we've drawn or considered, we have our net force. So that's the overall effect. And that's what we're trying to figure out. And this one's going to work out really simply, but I think this modeling of the math when the problems get harder is a good strategy for you guys. So I'm going to go through each force and kind of determine which way it's going and how big it is. So if we start with gravity, gravity, is it going in the x direction or the y direction? So again, I'm just going to kind of connect it. So there's gravity. And it's pointing down, so that's going to be in the y direction. So the x direction is going to be 0 because it does not go left or right. And the whole amount of gravity is going down, so down is negative, and that would be -3. All right, so that's how you would do the first one. For the applied force, that's going to be this one, going to the right. So the applied force, it's going right, so it's going to be positive in the x, and it's all of it, so that's 5. It's not going in the y, so that one's 0. For the next one here, for the normal force, that's going up. So it's not going in the x, that's 0, and the y, it's a +3. And then finally, the last one here, which is the friction force, is going to the left. Left is negative in the x, and it's 5, and then it's nothing in the y because it's not going up or down. So we've labeled all of our forces here, and we've did their components, and now all you have to do is add. So we're going to add all these up, and just like you would predict without this chart, because this is a lot of math for just saying, oh, this cancels that, The horizontal forces cancel, the vertical forces cancel, so the net force should be 0. So if I add up these columns, 5 and -5 get me 0, -3 and 3 get me 0. So the net force, F net for the first one, is 0. And what that means is the object, 0 newtons, the forces are balanced. It's not going to accelerate. It's not going to change its motion. It's going to do whatever it's doing. So if it's staying at rest, or if it was at rest, it's going to stay at rest. If it was moving, it's going to continue to move in a straight line at a constant speed, and we'll learn about that with Newton's first law. So that is sort of the way that I would suggest working through these with a chart. And I'm going to come back to this. When forces get a little more complicated, when things start going at angles, it's useful to be able to do that kind of work. All right. So for the next one here, it's similar kind of ideas. I'm not going to do the whole chart because it's not necessary. So we have 3 going up and 3 going down, so they're going to cancel. So the net force is just this friction force. So the net force in this second example is going to be 5 newtons going in the leftward direction. So that is the net force answer for that. And we can just see that when it's simple like this, we can just visualize it and say, oh yeah, it's just 5 going to the left. So the net force goes to the left, the acceleration is going to go to the left, and that's the idea. Okay. So sometimes you'll be given a net force and some other forces, and you're gonna have to solve for missing forces. Okay. So in this one, the net force is 0, so that means that everything is balanced. So if we look at these forces, we got this 200 force going down and B going up. So if this is 200 going down, how much is B going to be going up? That's going to be 200 going up to make it work because they're balanced, right? They're canceling each other out. And same with A. So A, the arrow got cut off. But if it's 50 going to the right, this is going to be 50 going to the left. So B is 200 newtons going up, and A is 50 newtons going to the left. All right. For this one, this example here, it's a little bit trickier because we have a net force. So again, if you want to do a chart, I think that is not a bad idea. So we have force C. We'll call this gravity just because we'll just think it's a gravity force. And both those forces are in the Y direction. So I don't worry about the X. In the other chart, I had X and Y. I only have the Y here. But I do know my net force. So my net force is 900 newtons going up. So it would be 900 and it's positive. My gravity force, I know that's 200 down. So that's going to be a negative 200. And we're going to try to fill in this box. So this box at the top, FC, that's an empty box that we're trying to figure out. So some number minus 200 gets me positive 900, and these are not to scale. So this arrow should be much bigger going up in our scenario here. And some number minus 200 to get to 900 would be 1100. So 1100 minus 200 gets me 900. So this would be 1100 for our force, 1100 newtons going up for force C. 200 going down for our force gravity. And you can see obviously like this one's bigger, that's going to win the tug of war, the net force is going to go up. Like that makes sense. All right. So the next one here is 60 going to the left. We got 2 dimensions, we got the X and the Y. And again, you don't have to draw these charts every time, and I'm getting a little bit short here. So I'll say FD, FE. We'll just say this is 80 going left for this one. It doesn't have a label, but it's negative 80 because it's going left, and that's there. And then this is a 0 and positive 300. These weren't labeled, these 2 rows. So like, I don't know, I could call this F B and F A. It doesn't really matter. Just so we have things to refer to. So FA, FB, and then we're looking at FD and E. So the net force is 60 left, so this is going to be negative 60. Since it's only left, that's going to be 0 for our net in the Y. So we got to figure out these numbers. So if it's only going left, what do we know about the up and down forces? They should cancel. So this is going to be E is going to be negative 300. and it's 0 in the, that's an E, sorry. That's 0 in the X because this is pointing only downward. For D, this is supposed to be D, it's not going up or down, so that's 0. And then some number minus 80 should get you negative 60, so this is going to be a positive 20. And again, it's just kind of a little bit of algebra. It's just that tug of war. So again, this arrow should be bigger, and this is going to be smaller. And the net between those is going to be 60 going left, which is what we said here for the net. And then for the last one here, I'm going to skip that one. It's more the same. They don't give you quite enough information. If it's only going to the right and it's 30 to the right, this would be 50 for G, because 50 minus 20 gets you 30 going right. And then F and H are balanced. They don't tell you what one is or the other one is, but they got to be equal to each other. Okay. The last one here is dealing with an angle. So I wanted to show you that, and we're getting close to the end of the video. So, and just show you how vector math kind of comes back into it. So I'm going to draw a picture, or a free body diagram for the picture. So it says a rope is tied to a sled and accelerates to the right across a field. So the tension in the rope is 10 newtons at an angle of 12 degrees above the horizontal. So 10 newtons, and that's at an angle of 12 degrees. So I'm just writing in 12, and I'm going to label this FT for tension. Just to have a set of axes here so you can see kind of the X and the Y axes. There you go in red. It says the weight of the sled is 5 newtons. So we have a force going down, which is the force of the weight, which I just call gravity. There is a force of friction, which is 2 newtons going to the left. So I'm going to draw that in. I'll use a different color. So that's going this way. And that's the force of friction. And then there is a force from the ground pushing up. We're not sure how big it is, but essentially, let me draw this a little bit bigger. They should be to scale. So if this is 2, this is supposed to be bigger than 2, so that might be 5, like twice the size of that. And this actually should be larger. So let me make this a little bit bigger too. The better your sketch is, the better inclination you get, or visualization of kind of what's happening to it. Let me erase that whole vector from here. So if you draw everything the same length, it doesn't really give you an idea of what should happen. So 12 degrees is pretty small. So that's like that. So, and that's larger, so that seems okay. So it's not exactly right, but it's okay. So that's tension. And then we need the normal force. So the normal force is from the surface pushing up. We've talked about that. It's perpendicular to the surfaces, so it's basically the normal force stops things from falling through each other. And I'm going to have that arrow going up here because it's a horizontal surface. So we need to kind of draw a free body diagram, which is what we just did. And we're going to set up our table, and we're going to figure out what is this normal force and what is the net force. So let's go ahead and try to set up our table and make sense out of it. So we got X and Y. And because this one has an angle, we're going to have to do a little bit of trig. So I'm going to review that really quickly here. But we add up all those forces, and we will get the net force here. All right. So just labeling the different things, we got the force of tension, which is going to be the one that is the most difficulty. Force gravity, force friction, and force normal. So what I like to do before I get into like figuring out math, I just do plus minus 0. So what I do is I say, okay, this force is directed to the right or to the left, or it's not directed right or left, and that would be a 0. So if it's right, it's positive. If it's left, negative. Or up, down, same thing. Up is positive, down is negative. So this tension force is going up and to the right. So that would be positive in the X, because right is positive, and it's going up, so that's positive in the Y, so that's also positive. The gravity force is not going in the X, so that's going to be 0, and it's going downward, so that's negative in the Y. Friction is only to the left, so that's negative X and 0 in the Y. And then finally, the normal force is not going in the X, so that's going to be 0, and it's positive in the Y. According to our problem, it says it accelerates the sled to the right. So it's not accelerating it up or down, it's just accelerating to the right. So the net force should be positive when we get that value, is what we would expect. And because it's not going up or down, it's not accelerating up or down, that value for the y is going to be 0. We know a lot of these numbers already. So it says gravity or weight is 5, so I can put that number in. Friction is 2, so I can put that number in. And then the other boxes are what I don't know. So the tension, it actually tells you a lot of the values that you need. It just, it doesn't give you the x and y components. So essentially, if I redrew this blue vector going like that, we're going to figure out, if that's the tension, we're going to figure out the tension in the x, or how far it goes across to the right. So that would be ftx, which would be this box. And then we would find fty, which is how much it goes up. Which would be this box. So again, you're going to be able to do that the same way that we did with projectile motion and finding the components of an object fired at an angle. So we're going to take the length of the vector for the tension one, which is 10, and multiply it by the cosine of the angle for the x, so cosine of 12 degrees. And then for the y, it would be 10 sine of 12 degrees. So if you put 10 cosine of 12 in your calculator, that'll get you the x. And I got 9.8 for that. So I'll put 9.8 here. And we said it's going up. I'm sorry, it's going to the right, excuse me. So that's positive, so that's fine. And then if you do 10 sine of 12 degrees, you'll get the y component. It is going up, so I'm going to write another positive here. So it just matches the signs that I had before. And this one, I'm just going to round to 2.1. Okay, so so now it's just like we talked about before. You're solving for a missing box. So if you have one box in either row, you can solve for that. So these blue boxes that I am highlighting here are the things that we are looking for. So the normal force would be this box. So if I do negative 5 plus 2.7 or 2.1, I get 2.9. So the normal force is 2.9 newtons going directed upward. So that's the answer for that one. And then for the net force, I just add this column, so it'd be 9.8 minus 2, which is going to be 7.8 newtons. All of these boxes are newtons, so even though I didn't write them in for unit-wise, all forces are measured in newtons. I don't think I mentioned that in the video. Okay, so there's one more slide here, and it's just kind of asking you to look at free body diagrams again. So it says the net force on an object points to the left. So the net force is going to the left. Two of the three forces are shown, so F1 and F2, and we got to figure out the third force. So we want the force to just go to the left, and which one of these would make the net force only go directly to the left. So let's think about these. And if you look at these arrows A, B, C, and D, they all look longer than 1 and 2, so that's okay. But if you start plugging in different ideas, so if you put A here, it would go like that. Is that going to make it just go left? I would say that's not probably right. So because it looks like this one would go left and up, so that's not going to happen because that's going on. If you did this one here, that's still going to go left and up, so I don't think that works. C is going like that. So the leftward part, that seems to work, and then this up and down part, they seem to be canceling out, so that might work out. If we try the last one here, D is just going straight down. So again, these would cancel, so I would think this would go right and down. So I think C is your only one that has the opportunity to do what you want it to do, and that is the correct answer. So in order for it to only go left, the up and down forces need to be balanced, and this X component for the third force has to be larger than F2. So that's what happens, and that's the right answer. So hopefully that first lesson on force and free body diagrams is helpful. It is drawing free body diagrams well, and understanding free body diagrams is probably the most important skill to be able to understand how forces combine to affect objects in motion. So have a great one. I will see you soon.